Hello everyone. My purpose today is to introduce our paper, namely, D3still, Decoupled Differential Distillation for Asymmetric Image Retrieval. As shown in Figure 1, in traditional image retrieval systems, users upload query images from edge devices to a platform server. The platform server utilizes large deep networks to extract features from the query images, which are then used to search within the database. This process requires massive network inference computations and significant network bandwidth. For example, when the network resolution is set to 256 and the large model is ResNet 101, the image retrieval system requires 192 kilobytes of network bandwidth and performs 12.99 G flops. As shown in Figure 2, asymmetric image retrieval systems present a compelling alternative by effectively balancing performance and efficiency. This system initially employs a lightweight network on edge devices to extract features from query images. These query features are then uploaded to a cloud platform, where they are used to search the database. For example, when the feature vector is 512-dimensional, the system requires 2 kilobytes of bandwidth, and the cloud platform does not need to perform model inference calculations. As shown in Fig. 3a, previous knowledge distillation, KD, based asymmetric image retrieval methods usually involve optimizing the distance between each pairwise similarity in the student, query, network and its corresponding similarity in the teacher, gallery, network. However, the limited representation capacity of the lightweight query network often leads to mismatches in retrieval orders. Our analysis suggests that enforcing strict feature representations on two networks with differing capacities inevitably encounters a notable upper limit. In image retrieval, the focus should shift from detailed image features or similarity scores to the order in which images are returned. We propose a novel distillation objective centered on the differential relationship between pairwise similarities, emphasizing consistent retrieval orders rather than exact feature similarity, as illustrated in Fig. 3b. We design a pairwise differential distillation loss function to ensure consistent retrieval order between the lightweight query network and the large gallery network as follows. From EQ1, our method involves the relationship between two sample pairs and simultaneously optimizes two sample pairs. Thus, our method can greatly reduce mismatched signs between two sample pairs to constrain the order of pairwise similarities between two networks to be consistent. Moreover, different from pairwise similarity knowledge that one-by-one strict constraints pairwise similarity between two networks, our method loosely constrains the relational difference of pairwise similarities between two networks to be consistent. This is because even if the query network with low capacity cannot strictly constrain the relational difference between the pairwise similarities of the two networks to be consistent, the retrieval ranking of the query network is still consistent with that of the gallery network. Consequently, in asymmetric retrieval, our pairwise similarity differential knowledge would ensure a consistent retrieval ranking between the query and gallery networks better than pairwise similarity knowledge. We decouple the pairwise differential distillation loss function to form a feature distillation loss function and a pure pairwise differential distillation loss function. The formula for the each distillation loss function is as follows. Furthermore, the query network must decide whether to focus on learning pairwise similarity differential knowledge from hard or simple samples due to the limitation of representation capacity. To evaluate the sample difficulty, we calculate the ranking consistency between samples as the indicator. Thus, the pairwise relationship distillation loss function can be decoupled as follows. As shown in Figure 4, we construct a decoupled pairwise similarity differential distillation D3still framework for asymmetric retrieval, which transfers feature representation knowledge and pairwise similarity differential knowledge from the gallery to query networks. From Table 1, it is evident that the asymmetric image retrieval method significantly decreases the computational burden of the query network compared to symmetric image retrieval. Specifically, the asymmetric image retrieval method reduces the inference consumption of the query network from 12.99 G flops to 0.25 G flops, making it feasible to deploy the query network on edge devices. Moreover, we observe that pairwise similarity knowledge slightly improves the query network's retrieval performance because pairwise similarity knowledge partially maintains retrieval ranking consistency between the query and gallery networks. Finally, the retrieval performance of the query network has been significantly improved when decoupled pairwise similarity differential knowledge is transferred from the gallery network to the query network. From Table 2, we can find that pure relationship distillation methods, i.e., RKD and PKT, that perform well in symmetric image retrieval cannot improve the performance of the query network in asymmetric image retrieval. This limitation arises from these methods only transferring relationship knowledge while neglecting feature knowledge, resulting in a misalignment of feature representation spaces between the two networks. Moreover, D3still significantly outperforms these distillation works, i.e., CSD and RAML, that transfer pairwise similarity knowledge. For example, when using ResNet 18 as query networks and ResNet 101 as gallery networks, on the MS-7017 dataset, D3still outperforms RAML by 1.82% map and 4.2% R1. Even when widening the semantic gap between the query network and the gallery network, our method consistently achieves superior performance. For example, when using ResNet 18 as query networks and SwinTransformer v2, Tiny, Swin v2, T, as gallery networks, D3still exceeds RAML by 1.84% map and 3.33% R1 on the SOP dataset. These experiment results can demonstrate that our D3still framework achieves state-of-the-art performances across all various network structures on 3 benchmark datasets. In conclusion, we design a pairwise differential distillation loss function to ensure consistent retrieval order between the lightweight query network and the large gallery network. Then, we propose a decoupled differential distillation, D3still, framework for asymmetric image retrieval, which transfers feature representation knowledge, inconsistent pairwise similarity differential knowledge, and consistent pairwise similarity differential knowledge to the query network. Extensive experiments demonstrate that our method is superior to state-of-the-art approaches.